the last thing that we did was I introduced the notion of a primitive nth root of unity. And what that is just something whose nth power is one and no lower power between 0 and n gives you one. Well, so give you this first proposition here. So I'm going to talk very quickly about kind of these cyclotomic extensions and give you kind of a little folklore, well, more than folklore. Let n be a positive integer. And a field containing primitive n root 1 number 1 if d divides n then if you look at this thing, so d is a divisor of n. So if you look at this to the n over d power, this is a primitive d through 1. And 2, if d divides n, and u is a root of the polynomial x to the n minus a in kx. Oh, that's d. So if d divides n and u is a root of x to the d minus a, then x to the d minus a has d distinct roots in ku. In ku. And not only that, ku is a splitting field. Yeah. Minus a. Okay. Ku is delta over k. And is cyclic. Okay, so let me kind of talk through this a little bit. So first, let me note that certainly this thing right here is a root of 1. And why is it primitive? Well, so if well, this means that then D divides K. Right? So um, right. So notice if so therefore since K over D, and of course we can assume that K over D is an integer. So therefore K because then K is in this interval. This is clearly not an integer. So this must be primitive. For this, let me point out that
Why do we know that the defined state?
well, so here's the deal. We have whatever it was, in K over D. Therefore, right, so that has been info. Let me make a remark on this. If U is a root of this, so for the second part, you have U to the D equals A. Then the roots are U they're your roots, because of course the deep power of U is A, and the deep power of any of these, well, what we have is primitive D root unity times U. You take any of these to the deep power, you get 1 times U to the D, which is A. So these are all the distinct roots. It's clearly distinct because we have different powers of the primitive root unity. And of course, we see that K of U is a splitting field because by assumption, I did look that up there, didn't I? Yes, K contains this little tornado guy. So when you adjoin U, so when you adjoin the D through A, you've already got this thing in here, so you have all these powers of tornado, and so once you get U, you get everything else. We saw actually something similar when we did these various things like in homework set we did X and fifth minus 3 and so forth. Once you get that root of unity, you get all the other roots. Right. And the Galois group is cyclic. You should probably check that out. I either missed an assumption in this thing, or I corrected this on the fly. It said that in my notes it says that it's cyclic over D. What's wrong with that statement, given the way that I wrote the proposition? it's not necessarily cyclic order D. It's cyclic of order less than D, because, for example, what if the polynomial was x to the D minus a to the D, right? In this case, the root u would be a, and it would already be in there, right? So in this case, it certainly would be Galois, it's a splitting field, but the splitting field is just the field itself because the polynomial is not irreducible. So if you put in irreducible here, then you'll get, I don't think I said that process. Yeah, if it's irreducible, then or D, otherwise it's a little less than D. Theorem. Theorem 8.7.10. Let F be a field extension of K, and K contains again a primitive nth root of unity. And K is contained that. So K is just some field that contains a primitive nth root of unity, and F is some field extension of it. Let me give you an example. For example, if K is Q, then certainly Q contains the primitive square root of unity, right? Namely -1. The following conditions are equivalent. Number one, F is cyclic of order D. So in other words, we're called what I mean by cyclic. It's Galois, and it's Galois group is cyclic, where D by 10. Say that. 2. F is a splitting field over K. Of a polynomial. Of form x to the n minus a x. F is a splitting polynomial form where D by 10. Right. Notice the 2 implies 3, right out of the gate, because if it's a splitting field this form, then certainly this is true because you can just take it out of the end, right? How about 3 implies 1? Well, suppose it's a splitting field of such a polynomial. We already know that this polynomial has D distinct roots. Previous one, so therefore it must be Galois, right? And Notice that if you adjoin one root, you've got all the roots, because the roots of this polynomial are c to the 1 over d. So if and so this is very similar to 4. This polynomial we already know has these distinct roots. There's the list of them. These are all in this is a subset of a K going to C to the 1 over D. And this thing is the splitting field. So it's Galois and see if you can show that this is in fact cyclic. This is similar to homework exercises. Notice that once you decide, these are the D roots, and it's got to be a permutation. Once you decide which one this goes to, that determines the rest of it. And from that, you can get that it's cyclic. Now I'm going to specialize something called cyclotomic extensions. Sounds like cyclic. In fact, it's a specialization of this. Informally, what this is, cyclotomic extension is just the splitting field of a polynomial form x to the n minus 1. So it's a very special kind of, notice with all these kind of ones that we looked at here, we're looking at polynomials like this. Cyclotomic extensions are basically splitting fields of the polynomial x to the n minus a, where a is 1. So we're looking at a very special type of polynomial. Definition. 8, 7, 11. And then we'll make a couple of observations here. I want to do some examples here. Lacavia field. We define a cyclotomic extension of order n. I want to use this convention of order n, although I find this a little bit, this is not the best terminology in the world, and I'll explain what I mean by that in a moment. Of course, your order refers to the degree of the polynomial that I'm taking apart. What can be misleading about this is when you say cyclotomic order n, that doesn't necessarily mean that it's order in the same sense when we talk about cyclic extension. So, for example, okay, so let me look at various cyclotomic extensions. Okay, so I'm going to use this. This is sort of the n primitive root n, right? So another way to think of this, if you're a fan of complex variables, you can think of it this way. All right, since I'm talking about specific with you. So notice that And the cyclotomic extension when you join one to the primitive square root of one is this. So the splitting field just needs to pick up this. This is also right. Nothing new. Irreducible polynomial. Irreducible polynomial of the primitive. Of course, this is the root. So the polynomial this comes from is x cubed minus 1, right? One of those roots is 1, which is boring. And the other two actually come from this irreducible polynomial here. And the degree is order 2. Oh, this example. So if I look at the splitting field of this, then if I join a primitive fourth group unity, this is Q of I. And the degree Q of I over Q is equal to 2. Uh, uh, Anybody know what this one is? You have experience with this, I think, in the homework. Well, this polynomial, I believe, at some point you proved quite irreducible of Q, right? And this has a primitive fifth roots at the end. So once you get one of the roots, you get them all. It's pretty straightforward. How about this one? Let's look at this polynomial. If I join the primitive root, so it's there. These roots are already there, so they don't count. This is quite familiar, shows up here. Second two. This is only a quadratic extension because cheater. If you have a root of this, you have a root of this and vice versa, right? Because any root of this, this is a cube root of -1, right? Which is basically right. So if you have the cube root, this thing is cube root 1. If you change the sign of any of those, it'll be a cube root -1, right? And so once you have these roots here, you got these and vice versa. Dare I do it? How about this one? Oh, this is complicated. Let's see how to package this. This is x squared cubed. Right? So this should be the same as x cubed plus 1, except plus x squared. I'm going to take a stab at 3 with this. So take a primitive one. Notice if you have these roots, you got these roots vice versa. Went through that before. And notice that basically the roots of this, the square root is this. Because you replace x by x squared with this, right? And also notice you've got plus and minus sign. That one. Yes. Yeah. It actually be cyclical 4 and it'll have, so it'll have the big field, and there'll be an intermediate field of degree 2, which I bet you can guess what it probably is. And right. So let me give you a theorem. Does anybody see what the pattern here is? Yeah, that's so let me give you a theorem that encapsulates this. Let n be a positive integer and n a cyclotomic extension of k order n. Let me say that a little bit better. Let f be splitting tool. X and minus 1 of k. Um, right, and we will, number one, F equals K, when tornado, where tornadoes permanent been through one. So there's no surprise here, I don't think, because if you let, and of course, let me also say, if a primitive nth-root one exists, that's assuming primitive nth-root one exists, because, for example, if this were x squared minus one over field characteristic two, there is no primitive square root of one, right? I mean, this, because it's a solution of x squared minus one, that's x minus one squared. So assuming that you have a primitive nth root, it's that. Once you have that primitive nth root, then you get all the roots of this because all the powers of that primitive nth root, the other roots. F is an abelian extension. Okay. Of dimension. Well, we clarify this with degree of F over K D, where D divides Euler field in, and I'll explain that in a minute in case you don't know what that is. And n is prime, F is cyclic over K. And finally, 3 or the Galois group that okay, whatever you want, is isomorphic to a subgroup of roots of Z, and that connects with the Euler phi function there. So, how many of you remember? I guess usually we have at least two, but how many of y'all remember this? Okay, just make sure. This is actually I use the C mod one. Well, actually, I use this. So just count the number of elements between 0 and n minus 1. That is the elements of z mod n, which ones are relatively prime n. So for example, because if you go 0, 1, 2, 3, all the way up to p minus 1, everything's relatively prime to b except for 0, right? And anybody know what this is? What I don't know what this is. Well, actually, for this one, it might be best to count the things that aren't relative prime. So let's go from 0 up to look at all integers in that interval. Let's count how many things actually have a factor of p. Well, 0 does, p does, 2p does, and all the way up to, I guess, p to the m minus p. Everybody agree? Well, how many of those are there? Well, it looks to me like, let's see. That's the first, or actually that's the second, that's the third. So if you divide by p and then add 1, that's the number of elements. So right. So the Euler phi function of p to the m should be p to the m, that's how many elements are, minus, take away the ones that have a factor of p. So this is p to the m minus 1, it's p minus 1, which is a nice generalization. This. Notice that when you equals 1, you get the previous. All right. And also, it can be shown fairly easily. The Euler phi function is multiplicative over relatively prime things. So really, if you look at the Euler phi function of n, another way to think of this is this. You can also think this counts units in Zn. Right? Because what it's doing is it's rattling off everything that's relatively prime to n, and those are actually the units. And that's the connection here between part 2 and part 3. Okay, any questions? So let me give you a couple of last remarks. Let me point out kind of an interesting. There is a famous theorem by Kronecker and Weber. that if F is an abelian extension Q. Okay, so what I mean is, it's an extension of the rational numbers, it's Galois, and it actually has an abelian Galois group. Then F is contained a cyclotomic extension. That's kind of nice because what that means is if you have F that is any abelian extension, then if you get big enough, if you have N big enough and have a cyclotomic extension for N, you'll find that F is contained in there. So you can put it in. So in other words, every abelian extension is contained in some appropriately large cyclotomic extension. A word of caution, this is not true in general for extensions. So even though this fact is true for Q itself, if you have an extension of Q, this may not hold. Let me also make another sort of definition here.
When you
Yes.
say this is not true in general for extensions of Q, are you saying if we remove the word abelian, then it becomes not true, or are you saying we replace Q with something else?
You replace Q with an extension of Q, because this theorem doesn't hold. So you might have an extension of Q and an extension of that that's abelian. It's not necessarily contained in the cyclotomic extension of your field that you replace Q with. So we say F is radical extension of Q. Okay. If U1 to the M1 is in K. So this first thing that you can join, there's a large enough power of this back in K. And for all J bigger than 1, U J, the MJ is actually in K, U1, U2, UJ. So what this means is this is generated over K by U1. Say the M1 power gets you back in here. The M2 power of U2 is in here. The M3 power of U3 is back in here, and so forth. this is what we call a radical extension. Let me give you an example. We've seen some examples of this. We've seen some short ones, right? Here's another change. Notice that clearly the cube of this is contained in Q. And actually, this is a primitive, in fact, let me write it, do notation here. This is a primitive cube root of 3. And so the third power of this is in Q, so in particular it's in here. Same with this chain here, the fifth power of this is in Q, and the fifth power of this is in Q, so in particular it's in here. So these are examples of radical extensions. Radical extensions can be so you can refine radical extensions to chains like cyclic extensions, as a matter of fact. Let's not do that. Let's do that. The problem, the reason I don't say this is, of course, this is, you're tempted to say this is a cyclic extension because the cube root of this is down in here. But the problem is this is in Galois, right? But the point is, can anybody guess what's important about radical extensions? Why I would even bring that up? Well, let's say that you have a polynomial over K, and this is its splitting field, right? If you have this situation, then you can write every root of the, so you start with an irreducible polynomial K, and this is the extension that contains all its roots. So all the roots are sums, products, quotients of things in here, right? Do I agree with that? But notice that basically you can express everything in terms of radicals, that is perfect roots, right? Because U1 is here and U1 is the cube root or the M1 root of something in here. So everything in here can be written as sums and products of nth roots, right? Well, now this U2 can be written as sums and products of the M2 roots of this thing. So you can translate that down as the sums and products roots of this. So everything in this extension can be written as sums and products of perfect radicals. These are the kind of extensions where you actually have a formula, right? So if I have a polynomial, like for example, and I can get to a splitting field by a chain of these just perfect roots, that means every one of these roots can be, and there's a formula for this, right? What does it take for this? Well, basically, what it takes for this, if you think of the Galois correspondence, let's suppose this big one is Galois over here, and you've got Galois root of G, Galois, or well, this K is fixed field of G, and this is the fixed field of the identity. This corresponds to a chain of intermediate groups, right? And you can refine this actually to be abelian. So does anybody remember what it means if we have a group Well, I can always do it. And suppose that GI is normal to GI plus one. And GI plus one, GI is abelian. And G is, but remember what this is. But remember what kind of group has this property that there's intermediate chain salt. That's right. So this is really fast and loose for sure, but these towers right here, if you have this tower, it turns out that you can find this intermediate chain subgroups and get these abelian quotients. So G is solvable. Well, F over K is the radical extension. If and only if the Galois group F over K solved. And I should add the caveat. If F is Galois, then F over K is radical, F is radical extension of K, if and only if the Galois group is solved. That is why when you get Galois groups S5 and A5, for example, these are not solvable groups, then if that comes from a quintic, you can't solve it. But if you get the other three, F20 or D5 or Z5, it is solvable. So you might think about, like I said, this fast and loose, how does this connect with this quote or these the solvable series here? Then and if you can't figure that out, let me know. Any questions? I ran over today and I apologize for that. Any questions out there? Okay, well, we will see you next time.